You want to talk mostly about electrolytic?
Yeah, I mean, yeah.
Okay, so AP review session number 2, we're going to be using this book, and we're going to talk about electrolytic cells, which is on page 302. And so a couple things to understand about the idea of electrolysis. Lysis means to break apart, and so we're using electricity or energy to break it apart. And most of the time when we're breaking something apart, we're going to be talking about water. So a lot of times we'll have water inside these cells. Weird glare happening here. That did not make it at all clear. Okay, so anyway, do you have particular questions, or you just want an overview of what it is?
More of an overview.
Okay, can you handle that?
I remember electroplating, but maybe something else.
On electroplating,
Yeah.
specifically? So electrolysis in general, you're going to have 2 different probes or metals or something that's sticking inside there. They tend to be something that is inert and just means that, and inside here, you'll still have an anode and you'll still have a cathode. But you'll also, because water itself isn't going to be enough to make this reaction happen, you need to have ions that are in there as well. And so one we used an example of was like our Na+ ions and our Cl- ions, the idea that we salt into there. And that is an example of one that works, but there's lots of ones out there. This one's using the example they're using in the book. I'll go with that one. They're using copper sulfate, so Cu+2 and SO4-2, all in this water solution. And so you still have to have a connection, just like before, with your galvanic cells. But in the galvanic cells, we are making energy. In an electrolytic cell, you're using energy. So there needs to be some sort of power supply here that is forcing electrons to go through. So if we all the way around, you're going to move from one piece to the other. If my electrons are traveling that way, then you'll be able to label still your anode and your cathode, because the same process is always going to be happening. Your anode, remember, is where we're losing our electrons, and your cathode is your electrons. So we had that silly mnemonic red cat. So reduction is your cathode. Remember, reduction is gaining electrons. So this side's got to be our cathode, and this side's got to be our anode because it's losing electrons. What was the fact that they're both vowels. So anode is also oxidation. A and O, the vowels go together, and cathode is reduction. So the consonants go together. Just a way to help remember that. A lot of times they'll ask you to label what's happening. Okay, where electrolysis gets more confusing is because of these substances that are in there, you have to decide which of them will actually lose electrons and which of them will actually gain electrons. So you have to have that reduction potential chart and look to see what's going on. And since we've got electrons being lost on this, electrons are going away from your substance, what's going to happen to your anode? It's going to become positively charged. I guess I don't need to ask questions because it's losing the negatives. So that becomes slightly positive charged. And so my negative electrons, or pardon me, negative ions get attracted that way. So my sulfate is going to go toward, and since my electrons are being forced towards my cathode, where we're gaining those electrons, this side becomes negatively charged. And since it's negatively charged, my copper is going to be attracted that way. So copper is going to be towards the cathode side. But on both instances, I also have water. and water is on both places. So I have to figure out who's more likely to be oxidized, sulfate or water. Who's more likely to be reduced, copper or water. So first is to figure out which way the ions go by identifying their anode or cathode, and then deciding between the two.
No.
Okay. So the way we decide between the two is we have to look at our reduction potential chart and find the equations that most closely resemble what we're talking about. Sulfate tends to only have one possible equation that it's part of, and the one that I'm pulling out of the textbook, this helpful book, sulfate plus water, plus hydrogen ions, plus 2 electrons. And then makes H2SO3 plus water. I've got more room.
Where'd you get that equation from?
I pulled it out of this possible set of
Okay.
equations here on page 303, but you'd be given it in some sort of chart. And so then the one that they have for water Oh, I see. Okay, so this book jumped ahead of me. I was seeing the water potential. We've got H2O plus oh, I had the right one. So off the chart. Sorry, I was having trouble reading the chart there for a minute. But I've got my sulfate ion that's over here, the water molecule that's over there, as well as the 2 equations that go with it. Now, the thing that's a little bit tricky about these, for this side, sulfate and electrons are on the same side of the equation. So even if I flip my equation around and I write it as H2SO3 plus water, and I say that it makes sulfate, some electrons, and some hydrogen molecules, sulfate and electrons are still on the side. So when we're talking about something losing electrons, the idea is that molecule needs to break apart and electrons need to be left and released from that side. So one substance has them, and then on the other side it has to leave. So sulfate and electrons would have to be on opposite sides for to be oxidized. And I do not have an equation available to me in which sulfate is able to be oxidized. That's mostly because it's already got these 2 negatives and it needs to have that to be able to be stable. So that means to me that sulfate can't be the one that's participating in oxidation here because it doesn't have the ability to be oxidized. So that left me with my water is the one that's most likely to be oxidized here. This book also has you look at, it has you compare the copper ions, but it's not going to be the one that's oxidized either, so I'm not going to do that. Then in the reduction side, we do have them so that water can gain the electrons and turn into something new. Copper can also gain the electrons and turn into something new. So they both have the ability to be reduced. So the next step is to compare their electron cell potentials and determine which one's more likely to be reduced. So we've got 0.34 volts versus 0.2 volts. And since we're looking for a reduction, we want to choose the one that's most likely to be able to be reduced. So we want the one with the most potential. So here we're going to use our 0.4 because it's higher up on the list than our water molecule. So that tells me that here, copper is going to be likely to be the one that's reduced on this side. Interesting. So this actually has copper being the one that is able to be reduced because it in fact does have plus two electrons is Cu solid. And so this form of your equation is the reduction form of your equation. So to show it as being able to be reduced, we have to flip this equation back around. So it's going to go from copper solid to become my copper ions and my electrons. And since as the previous version, if we were to compare negative 0.34 versus negative 1.23, copper is the one that has the higher reduction potential. It's the higher value. So that makes it the choice. So that's why they're actually picking copper, because when you look at your two equations, this one has the higher value. That's an unusual situation to have that actually occur. But it's the example he chose in the book, so we'll go with it. And then if you want to look at electroplating, that's what you wanted to look at, right?
Yeah.
You want to talk about that? Do you have any questions about this?
No. I was confused as to why it says by the water, because in the book it says
1.23?
Yeah.
Oh, you're right. It actually says 0.83. Jokes. I looked at the wrong one.
I was just,
Yeah, you should shout at me. Sorry.
I was just wondering if
No, I just grabbed the wrong one.
that's what I figured.
I just grabbed the one.
Yeah.
0.34. The 0.2 was for the sulfate. I just looked at it wrong. Sorry.
Okay. Good.
Other questions? So another thing the book does is he also puts the sulfate one in this mix since it can only be reduced. So he puts it over here, but it still isn't as likely to be reduced as copper. So it's a good thing to check for.
How come it can only be reduced? It's just
because like I was talking about how they're on the same side of the equation. So your electrons are always going to come together with sulfate, or sulfate's going to be apart, but it has to be reduced. Okay, so then we're going to talk about electroplating. This one is the one people tended to like a little bit more because we're looking at stoichiometry.
Yeah.
So most of the time you have to be given some values and just be looking to match up your units. But you have to remember a couple variables, I suppose, that goes with it. So we're on page 304 when we're looking at that. Let's see what their AP tip is. Okay. So what they're saying in your AP tip, this is what I was talking about, this AP tip here. They're talking about the fact that your plates tend to be inert. So in order for copper to actually be able to be the one, how I said it doesn't usually happen, that copper is going to be oxidized and reduced, that is only going to happen if your electrode is actually made out of copper. So copper has the ability to be reduced as well. Since most of the time you don't have that, then copper wouldn't have been an option to be able to be reduced. So that's what they're saying in that tip, that it doesn't usually happen, but they happen to give you an example just to be mean, I guess. So just kidding. Whoever sees this on the internet, it's a lovely book. And so we want to remember a couple of things: what an amp is, Faraday's constant, coulombs, how those all kind of relate together. And that's what they have there right before the example. So the unit A, which is our amps. You've got C, which are coulombs. I may have spelled that wrong. And Faraday's constant. You, I believe, get all of those on the AP test. So you just need to make sure you know what they are and kind of where you know. But the idea of your amp, that's going to be how many coulombs per second you would have. Trying to decide if I spelled coulombs wrong. I did. Faraday's constant here is 96,485 coulombs. Spelled it wrong again. Is how much moves per 1 mole of electron. Mole or one? Yeah. And so our coulomb can just be our tool that we use to be measuring our electron movement. So if we had a question that says something like, you've got a current equals 1 amp. So 10 amps. Jokes. 10 amps. And then it's passed through a solution which has a +2 charge. And it's passed through for 30 minutes. It produces 5.94 grams of our unknown metal. The question is, what is the metal? This is a really common question to have been asked. So if you look at this question and you think to yourself, I have nowhere to start, the best place to always start is stoichiometry. So you've got 3 number choices: 10 amps, 30 minutes, and 5.94 grams. And the question is, which of those do you start with? We can't start with amps, should come next. You can either start with minutes or we can start with grams. Now, the thing that's tricky about that is neither of those are conversions. So you just have to be comfortable with the idea that I would encourage you to start with your minutes. And the reason is, why do they give us grams? Well, in order to know what our metal is, what's the best way to identify metal? Any guesses? Nope. And we knew its molar mass. So we want our molar mass. And so we can know the number of grams over the number of moles will tell me what its molar mass is. So I know how many grams were made. Now I just need to solve here for my number of moles. So this number is already going to be used later in the game. And so that's how I knew my winner is, I'm going to start with my 30 minutes. So if I start with our 30 minutes, somehow you want to get it to seconds, because that's what my values over here are talking about. So in 1 minute, there's 60 seconds. And so then I need to get from seconds to something else. And so probably the best place to go would be to coulombs. Since I know how many amps I have, I can make that conversion. Since it's 10 amps, the same thing as 10 coulombs per every second. So now my seconds are canceled. And then I need to get from coulombs to something. So my number of coulombs I can transfer can be Faraday's constant. For every 96,485 coulombs, I'm going to transfer 1 mole of electrons. And for every mole substance, thank you. Did it work for you?
Yes, good.
Thank you so much, Mr.
Appreciate
Beeman. Have a great day. Since I'm going to transfer, okay, so this is where it gets a little bit tricky for people. My substance, my unknown metal, is Nm plus 2. So for every mole of my substance, how many electrons are going to be lost? 2, because it's got a plus 2 charge. So I have 2 moles of electrons for every 1 mole of my M substance because of this plus 2 charge here. You can think of it like if we were going to write this equation, right? And we were thinking about it in terms of like a reduction potential chart. That's what they usually look like. My M plus 2 has to gain 2 electrons to get back to being that M solid. So those 2 electrons represent what needs to go here in the bottom of my chart to turn into 1 mole. So then when I solve this, that will be the number of moles that I was transferring. And if I compare the number of moles to how many grams were made, I can find my molar mass. Sense. So my molar mass can equal whatever I get when you divide it by that. I don't know if I have a calculator. They did it for us here. We'll just use their answer. So the number of moles they got were 9. I lost it. 33 times 10 to the negative second moles of my M. So I'm going to bring that over here and say it's 5.94 grams of M over 9.33 times 10 to the negative second moles. Because remember, molar mass is grams per mole. So I want to make sure I put it in that order. So when I get my molar mass, the book is telling me that the answer is 63.757. So then if you go to the periodic table, figure out what element would be closest to that, you would find out that it's most likely to be copper. It's probably copper, which works because you can have Cu plus 2. You could also do this in one step, and in the book, it shows you how you could have started with your number of grams because you put grams on top and have to have moles on the bottom, and you could work it out that way. You are welcome to do that. I just know that sometimes that's confusing for people. Okay, what questions do you have?
Will they give you that the molar mass, like they like
Just told it just says that in the explanation. So it is expected that you know on the test that molar mass is equal to grams per mole. So they ask, if they ever ask for the identity of something, a really common thing to do is to find your number of grams per mole. So the other questions here are like, do a titration, and you could figure out how many moles through a titration. They'll give you the number of grams, and you could divide it to figure out your molar mass also. So that's a common tool to use. See what their AP tips are. How comfortable are you with being able to recognize whether something's being oxidized or reduced?
Really comfortable.
Okay. This chart here on the top of 305, I think, is a good chart. It does a nice job of comparing the difference between galvanic cells and electrolytic cells. I don't know. It's a good one. You should check it out.
So why are the signs of cathodes and anodes different on the different keys? So,
Because on the galvanic cell, it's sending the way the electrons are transferring are different. So like in electrolysis, we're forcing the electrons to go that way. So we made our electrons go towards that, and then we made it gain. So it has a buildup of electrons and causes it to become negative. Whereas in galvanic cells, the compounds themselves are naturally losing in that. So when they're like substances around them are gaining its electrons, that causes the cathode to become positively charged, because as the electrode itself gains electrons, that causes it to pick up that mass, and the substances pick up those extra electrons, and so that charge is lost. Since it's losing its electrons, what's happening are the ions themselves are picking up those electrons, and that's causing it to become negatively charged. So it has a buildup of negative charges on that side. So you're thinking more about like what's happening within the solution on those. The E?
yeah.
So overall, remember your galvanic cells are positive, so their E value is positive, whereas your electrolytic cells are not. Did I say positive twice? I'm sorry. Your galvanic cells are spontaneous, so they have to have a positive E cell that's making energy, and so they'll happen naturally on their own. Whereas an electrolytic cell is not spontaneous, so you have to provide energy. So essentially they're absorbing energy, so they become negatively charged.
I lost my phone.
I'm sorry.
Okay.
I'm glad you remembered it. That sound like a good place to stop? Do you want to look at some of the multiple choice questions? It's your call.
Thanks.